Now, so now, Tim.
Great, thank you so much for the invitation. It's so nice to see all of you, even if it's just virtually. Yeah, I'm excited to tell you about this series of works that I've been doing with Dan Green, who's at UC San Diego, faculty there. He's my inflation guru. He's really the real expert here. And then his student Irscale Premkumar, who's been fantastic and is moving to University of Chicago for postdoc in the fall. And one of these papers involved Alec Ridgway. I'll highlight that along the way, who was a postdoc at UCSD. So we've really been, all of this work kind of stemmed from wanting to understand the long wavelength limit for modes in de Sitter space. And the applications here are wide ranging. So of course, we believe that there was a period of inflation that preceded the Big Bang. And so all of the formalism we're going to talk about is relevant for theories of inflation. And then there's also, you'll see another application here is we can also talk about light scalar fields in a de Sitter spacetime that are not the inflaton, and we can understand the dynamics of basically those scalar field fluctuations and the probability distribution that emerges. So, and finally, what this talk is, so I'll highlight a lot of this along the way and try to explain the story from our point of view, but I really want to highlight this most recent paper, The Tale of Eternal Inflation. Basically, we applied this formalism most recently to understand the dynamics of the inflaton in the presence of primordial non-Gaussianity, and we found a surprise. And we have some guesses for the interpretation, but actually are in progress trying to figure out if we can sharpen this. So happy to discuss the things we're doing in the future and thinking about now at the end of the talk. Okay. So let me set the stage here by explaining what the types of calculations we're going to be interested in are. So we're really going to focus on trying to come up with some formalism that allows us to compute the probability distribution of scalar field fluctuations of some field phi. Like I said, could be a scalar field, a light scalar field in de Sitter, could be the inflaton itself, as a function of time. And this is a very well-studied problem, and I'll highlight some of the classic formalism along the way. But the idea here is simply that there's some classical evolution, which is governed by a potential. So here I'm kind of highlighting what's relevant for the inflaton. So this is a very flat potential. So we have some classical drift that's pushing us down the potential, and then there's the so-called quantum noise terms, which are essentially, there are lots of ways to think about those, but you could think about, de Sitter has a horizon and a temperature associated with it that causes there to be thermal fluctuations of these fields, or you can think of this as coming from, fundamentally the fact that these are quantum fields and they fluctuate. Those are sort of equivalent pictures. And so the standard story is we're in a regime where the classical evolution dominates this quantum noise. Okay, and that's typically the setting for slow roll of inflation. And the field just evolves as a function of time. It goes down this potential, and then it hits some point where something dramatic happens, and that's reheating, right? All of the energy density that was stored in the inflaton potential is converted into some thermal bath. But if this probability distribution is very wide, this can happen in regimes of parameter space where the classical evolution and the quantum noise start to become of the same order. And what ends up happening is that some of the patches fluctuate wildly away from the reheating surface. If you like, there's now the quantum noise can send you this way with a non-trivial probability. And so those patches of the universe may never reach the reheating surface. And this is the scenario we call eternal inflation, okay? So if I go back, in this picture where we're very localized, our probability distribution is very localized, this distribution just all together hits the reheating surface and the whole universe reheats. In this picture, say this part of the distribution may hit the reheating surface, but this part as a function of time may get pushed further away. So there's always some patches of the universe that are inflating. And so that's the basic idea of eternal inflation. It was recognized as a limit of inflationary models from the beginning. And so here we're gonna have a way to talk about this in a pretty sharp setting. And you'll see this will lead us to this puzzle that I'll highlight at the end. So effective field theory is going to play a dominant role in this talk. And I want to start by reminding you of the now classic effective field theory of inflation. This is the effective field theory that emerges when you consider the fact that slow roll is giving you some time-dependent background, then that time dependence breaks diffeomorphism invariance. And there's a Goldstone boson associated with that breaking, which is what we identify as the inflaton. So that's the setting here. And you can see we've laid out the scales. So, gravity is important of scales of order m Planck. But then as we really where the EFT of inflation becomes relevant is at some high scale. Okay, here I've allowed myself, I'll introduce these parameters as we go along, but this is going to be a parameter that controls non-Gaussianity, primordial non-Gaussianity, which is effectively non-trivial interactions of the inflaton. So if you like, that's set by some heavy scale lambda. Then there's the pion decay constant, which is associated with this Goldstone boson, and that's essentially set by the time evolution, okay, phi dot. There's the Hubble scale, which is basically the energy scale associated with inflation down here. And then once you go past this point here where the change in the Hubble scale becomes appreciable, now de Sitter is no longer a good approximation. And so the theory is, starting to break down in this regime. Okay.
So sorry, Tim, can I ask a question here? So this,
please.
This spontaneous symmetry breaking, this is also referred to as natural inflation, but it's kind of ruled out by the Planck result. So is this just a toy model?
No. So this is different from natural inflation. So so here we're really talking about the claim is that this effective field theory is a universal description of the dynamics of single field slow roll inflation. So this is capturing, to a very large class of UV models that are where their dynamics are governed by a single light degree of freedom. That's what we identify as the inflaton.
But what's the spontaneous symmetry breaking? I mean, are you trying to get a flat potential?
No, sorry. The spontaneous symmetry breaking is the spontaneous symmetry breaking of diffeomorphism invariance.
Oh, okay.
From the So sorry that wasn't clear. So it's really governed by the background evolution, right? The fact that there's time dependence in the background.
I see. Okay, yeah. Thanks. Sorry. Thanks.
So this is all comes back to this papers of effective theory of inflation, sort of. Late 2000, right?
Correct. This is, and my referencing is not very good in this talk. I apologize for that, but this is like Chung et al.
Etc.
Yeah, exactly.
Sergey, right?
Exactly. That's right. So this picture's been around.
Can I also ask a question actually about
please.
the previous slide? So in principle, the evolution of this probability distribution of the scalar field, it depends also on the initial conditions, right? Of what we assume at the beginning. And do we have any idea what initial conditions to use in this setup?
Yeah, good. So in this talk, I'm going to always be assuming that the initial conditions are given by the Bunch-Davies vacuum. So it's just simple Gaussian initial conditions. But here, so you can think of, even in the simplest and the first models of inflation, like say you just have m squared phi squared potential, there are regions of the parameter space where m becomes small enough where the potential is so shallow that you can get into this regime where the classical evolution and the quantum noise are of the same order, that those fluctuations are of the same order. So this is, if you like, you can think of this as a limit of the parameter space, this effect can emerge in essentially any model, if you take the potential to be flat enough.
Okay, so we assume that the Bunch-Davies vacuum.
Yeah, we're going to assume Bunch-Davies for the talk. We're not going to be doing anything. Everything we're going to be doing is going to be extremely conventional. Okay, so we're really going to be trying to ask questions about just the standard evolution of scalar fields, be they the scalar fluctuations of the inflaton or just a toy model with a scalar field in de Sitter space or quasi de Sitter space. So something that comes out of this EFT description is that we have basically time steps which are governed by Hubble. Okay, and you can think about the classical evolution. Okay, is just given by the slow roll, so phi dot, normalized by the Hubble constant. Okay, and just using the parameterization of the EFT of inflation, this is related to the pi on decay constant squared divided by Hubble, okay, through this relation. And the quantum noise is set again by the temperature of the horizon. The scale of the horizon is set by Hubble. So roughly speaking, you can think of the quantum noise as being of order h. And if you're in this eternally inflating regime, that's where you have taken the pi on decay constant to be small enough that it's order Hubble. Okay, and so that's the regime where quantum noise and classical evolution are sort of the same order, and you start to end up in this eternally inflating situation. So one of the things we're going to do in this talk is we're going to take the naive EFT of inflation and we're going to add the first leading interactions. Okay, so we're going to just have some cubic interactions among the these pion fields, right? The fields that are the result of the spontaneous symmetry breaking, and that leaves the imprint of primordial non-Gaussianity on the CMD. Okay, so one of the benefits of this EFT description is that it allows you to parameterize the leading effects of non-Gaussianity, and so here we need to introduce a new scale because this is coming from some fundamental interactions. And now the scalings change a little bit. So we still have the same classical evolution, okay? But what I'm going to argue for you in this talk is we can show that there are a new type of effect that comes from these non-Gaussian interactions, which is we can get a large fluctuation in the tail of the distribution, and it scales also like f pi squared over h. And now this is the new effect that I'm going to try to convince you we can compute reliably. This new effect tells us that we can now enter the eternal inflating regime even when f pi is much bigger than Hubble. Okay, so let me just go back. In the absence of interactions, we only got eternal inflation in this region of parameter space. But now the claim is going to be that we can get potentially eternal inflation due to some large fluctuation of the tail. Okay, so that's going to, again, by the end of the talk, I hope to convince you that of how we do this calculation and show you some of the results.
Sorry, but is this a classical effect or this interaction?
No, so you can think of this as a sort of higher order quantum effect, but I'll show you how it appears in the. So what I'm going to do is I'm going to derive a set of evolution equations for this probability distribution using effective field theory. And then I'll solve them and I'll show you that that we get these large fluctuations. Okay. Basically, that the probability distribution includes this effects in the tails.
I'm just a bit confused since you don't say that it's quantum noise, right? So it's something else.
Oh well, that's partly because we have intuition for what this effect is, but one of the things that will come out of this is a puzzle, and so it's unclear whether or not the effective field theory description is capturing this correctly. Okay, so once I show you the calculation, we'll get into that interpretation, and you can see if it makes sense to that.
Can you? And what's the expansion parameter
of what f pi is, or how you're interpreting f pi?
Yeah, so
it's phi dot. If I was thinking about just chaotic inflation, m squared phi squared, what's your f pi?
So it's basically just the slow roll parameter.
Well, so epsilon, you're saying it's just epsilon? V
Yeah,
prime-
it's set by epsilon, right? And then to get the scales right, you use Hubble. So I don't know off the top of my head. I don't know the exact matching for that example. I should, but I don't. So basically, I think of this. There is a matching calculation, right? So in the fundamental theory, I have this scalar field phi, which is rolling down a potential, and in this effective theory, I have this. I just have a Goldstone boson description, and it's in the absence of interactions, it's a single parameter theory, essentially set by this parameter f pi. So you should think of f pi, right? I mean, you should think of f pi as essentially the scale associated with the slow roll, and the theory with no interactions of this Goldstone boson just captures the Gaussian evolution of the inflaton.
But isn't it this like m squared, phi squared inflation is just a simple kind of mechanical system of particle being stuck on the side, being retained by a huge what is called resistive force of H, right? So phi dot therefore should contain a forcing term, something like m squared parameter, right?
Yeah, but it's just dv d phi divided by 3h. If you just get it from the Friedman equation, that's all it is. Yeah.
The mass should enter.
Yeah, it does. It's
in the
dv d phi.
numerator, and in the denominator should enter something like the potential itself, right?
Yeah, it's the force divided by 3h. It just comes from the Friedman equation. It's 3h phi dot is minus dv d phi. That's all it is.
Yeah, exactly.
Which is m squared phi in this case.
Exactly. It's m squared phi divided by h.
But I'm just trying to understand your relationship between f pi and h, because I know in even that simplest model, I'll always have eternal inflation if I choose my value of phi large enough. So there's never an issue. You'll always have eternal inflation. So
yeah.
why do I care about f pi relative to h? That's what I'm asking. I mean, that's
good. So yeah, where did the initial conditions it's a good question. I
think f pi is something like the square root of h over phi. So I don't know if and even that's maybe a funny way of writing it.
Is it proportional to phi? Is it proportional?
It's phi over h, isn't it?
Yes.
It's square root of phi over h.
Yeah,
so it grows with phi, right? So it agrees.
Yeah,
that's right.
Yeah, but h goes like m squared phi
careful.
squared.
No, you have to be careful because well, if you want, it's like what Tony said. It's m squared phi squared over h phi.
Yeah.
So or it's m squared phi, which is the dv d phi divided by h.
Yeah, but h goes like m squared phi squared, doesn't it? It's the potential.
Well, the square root of that. H goes as m phi over m Planck.
Yeah. So the phi's cancel then.
Yeah, exactly. F pi. So yeah, like I said, I mean, f pi is constant given the fundamental theory, right? The inflationary potential in the fundamental theory, f pi is fixed.
Right, so it would be the mass times m Planck.
Yeah, it'd be little m. Yeah, it'd be little m.
Little m times m Planck.
It's
f
the little
pi
m
squared would be little m Planck.
Yeah, it's the little m that controls it then. Yeah.
Yeah. But Keith, your question about how the initial conditions like where I start on the potential feeds into this, into the EFT of inflation picture. That's a good question that I just don't have. I'm sure there's a good answer, but I don't know off the top of my head. I'll tell you if it comes to me.
Okay.
Yeah.
So could I also just quickly, so what's the expansion parameter? I assume it's not f pi over h then?
Well, yeah, so the, let's see, I have,
for this EFT, is
yeah,
everything
let
going to
me-
be given by f? Because if you're taking f pi to be much, much bigger than h, and that's the expansion parameter, then
so did I write the loop?
No, f pi should be in the denominator.
Yeah,
of
f pi is in the
the
denominator,
parameter,
exactly.
Right? It's just,
okay, yeah, okay, that makes sense then. Yeah, okay.
Yeah,
great.
I didn't
it
write
gotta
the-
be like in the normal Caro PT, it gotta be some momentum of a mode divided by f pi, right?
Exactly.
So then your expansion here is h over f pi.
Yeah, so the expansion here is in momentum over f pi, but then we're going to take a further limit, which is we're going to take the we're going to take the small momentum limit, okay? Because we're really going to be interested, we want to understand what's happening with the modes that have frozen out, okay? So this EFT, the EFT of inflation, is really describing the dynamics of the inflaton fluctuations, okay, as they cross the horizon. And then we're going to match that theory onto an additional EFT for the long wavelength limit, where you take the modes far beyond the horizon. So here you can take the momenta, as long as the momenta can be in this entire range, as long as it's below f pi, right? Your EFT is under control, exactly in the analog with the chiral Lagrangian.
Okay, so it is identical to the chiral Lagrangian.
Yeah,
so it's
it's
momentum over f pi. Okay,
exactly,
thanks. Yep.
exactly. And it's a derivative expansion, right?
Okay.
In the same
Mhm.
sense.
Okay.
It's just and I should have included the Lagrangian, I'm sorry, but the thing that's different here is that we've broken Lorentz invariance. So you have spatial derivatives, which are separate from time derivatives. So the structure of the EFT Lagrangian, you just have to be careful with the way you power count. But that's all sort of well understood in this paper, Chung et al. from the 2000s.
Sorry, I'm still confused a bit. So,
Okay.
so what is the condition for the eternal inflation? So I would say that if the phi dot h, so phi dot h controls the classical force, right? So that that parameter is the classical force of this inflaton. So if that is larger than the Hubble parameter, then I would say that the classical force wins against the quantum kind of jumping. So it is not an eternal inflation. So that means that in order to have the eternal inflation, I should say that phi dot h is smaller than the Hubble parameter, right?
Yeah, so in the
But then in that case, I will get that the f pi should be smaller than the h. Am I correct?
yeah, exactly. That's this picture.
Okay, so in the next slide, so you're saying that the f pi should be larger, much larger than the Hubble parameter in order to have the eternal inflation, but it is just the opposite.
So the purpose of this talk is to convince you that there is a new contribution which scales this way. So I have not explained that at all yet. And then if there is this new contribution, that there's large fluctuations in the tail, that large fluctuations in the tail could give you internal inflation, even if you're in this different regime of parameter space.
Okay, so you're saying that you will always have the eternal inflation?
No, so in the presence of primordial non-Gaussianity, there will be regions of parameter space where even if I have this limit of the inflaton potential, I can still get eternal inflation. Okay, so that's the purpose of the talk. I haven't explained that at all yet.
Okay, so if the inequality is the opposite, then that is the standard story, and you will have the eternal inflation. And you are saying that
no, I'm saying if I just have the Gaussian theory in the standard story, right? M squared phi squared potential, say. Yeah. Then eternal inflation only happens when f pi is order h.
So what happens if the f pi is too small compared to Hubble parameter?
Well, if it's smaller, then it's sorry. I mean, this would be less than percent. So eternal inflation, the standard story of eternal inflation happens when f pi is of order h or smaller.
Yeah.
Okay. The the claim that I'm going to make in this talk, although it's already been half an hour, so we'll see if I get there, is that in the presence of primordial non-Gaussianity, we're finding a new effect which gives us eternal inflation in a new regime of parameter space.
Okay.
So does that imply that if there are no non-Gaussian, or if the non-Gaussianities are small, this doesn't happen?
Yeah, so, well, okay, so let me just show you the, yeah, so this is the last slide. This is where we're headed, since you're asking these great questions, right? Basically, the Planck constraints, so this is a two parameter, this is the result, okay? So there are these two parameters in the, at subleading order in the EFT of inflation, the interactions. And the Planck constraints are given here in red. So, you know, the best fit value is somewhere like that. And the claim of the talk is going to be that we have found a new regime which overlaps with the potential Planck measurement in the future, where it seems like eternal inflation is happening. Okay, but these are these two parameters which control primordial non-Gaussianity at the leading order in the EFT expansion. So what I want to do is explain how we compute this region, and because that required us to develop some new technology, and then make some, you know, also explain why what we think is going on here, or what, you know, basically the interplay of the EFT approximation and the calculation to understand whether or not we can really trust this. Okay, so let me go back. Okay, well, I showed you the summary slide. Maybe let me just move on. Okay, so how are we going to approach this problem? Well, basically the formalism we're going to rely on is the well-known formalism from Starobinsky of stochastic inflation from 1986. And here is the picture of the potential, and we have this drift is the classical evolution of the potential, and then we have quantum noise, which could push us in both directions. And this is captured, according to Starobinsky, by a Fokker-Planck equation of this form, okay? So the time evolution of the probability distribution is given by this first term, which is capturing the quantum noise, it's proportional to Hubble. And then the second term, which involves the potential, okay? So that's taking care of the drift, okay? And this Fokker-Planck equation gives you the probability of phi as a function of time, okay? So you just solve this and you get the dynamics that we're talking about. Okay, so Starobinsky's stochastic inflation is assuming two things. So it's assuming the Gaussian theory. So we have Gaussian noise, and it's assuming a tree level potential. And so the question that we want to ask is, can we figure out how to systematically correct Starobinsky's approach? Because, you know, at some level, Starobinsky understood it very intuitively, this dynamics, but everything that they did was just in this simple tree level and Gaussian approximation. And so what I want to show you is how we can use effective field theory to include systematic corrections to this. Okay.
Sorry, but are those two things, like tree level potential and Gaussian noise, aren't they related somehow? No, the next. I
mean,
slide.
so I mean, your question is, do you expect loops to generate non-Gaussian contributions to the noise, right?
Yeah.
Yes, absolutely, and that's what I want to show you how to do. So so there have been, in recent years, there have been a few different approaches to trying to compute quantum corrections to this equation. We believe that we have sort of the most robust that lets us compute these corrections systematically to arbitrary order.
So those quantum corrections are going to modify the quantum noise, basically the source term, right, in this equation. That's what's happening.
Exactly.
Okay.
And it will introduce, I'll show you, but it'll introduce also, it will both correct these coefficients, okay, but it'll also introduce higher derivative contributions, okay.
Okay, but in principle, non-Gaussianity can also come from just interactions, self-interactions of the scalar field already at tree level.
Absolutely, yeah. So
okay.
But well, no, sorry, not here. So if you, for example, if you had lambda phi to the fourth theory in de Sitter, the tree level prediction of lambda phi to the fourth theory is this. So you would get this leading contribution to the noise, okay, and the tree level potential, and it would all be Gaussian. To see the non-Gaussian corrections, you have to go to higher order in perturbation theory. But again, that's a part of what I want to show you.
Okay.
So we have this. Oh, my screen didn't update. Oh, Zoom. Can you, you're seeing the slide that says Starobinsky, right? Not a slide that says leading order?
Yeah, that's Starobinsky.
We're seeing Starobinsky.
Let me just reshare. My goodness. Okay, there we go. So, okay, so at leading order, this is just the same equation, okay? And you can solve this for a fixed point solution. You can set the time dependence to 0, and you can find that the equilibrium solution that you arrive at here is just that it goes like the e to the minus 8 pi v normalized correctly, okay? The purpose of this is going to allow us to understand how to systematically correct this equation as an expansion around this equilibrium solution. So in order to understand how to go beyond leading order, we want to expand the Fokker-Planck formalism to include higher order corrections, okay? And the condensed matter community has understood this for a long time. The right way to think about this is to start from the Markovian assumption, okay? So you just want to assume that your fluctuations have no memory. And then you can write down a very general, very simple equation for how to understand the time evolution of the probability distribution. It's basically given by the probability distribution at this time step, integrated over all possible ways the field can fluctuate to a given point, divided by subtracting from that all the ways that the field from that point could go to all other points, okay? So this is sort of, as long as each individual time step is independent, then this is the general way to capture the time evolution of the probability distribution. So then you can perform what's called a Cramer's moyul expansion. It's essentially doing a local expansion, and you can express the right-hand side of this as some Taylor expansion in the fields phi, where this is basically just taking moments of these transition amplitudes. And what that tells you is that you're going to organize the corrections as follows. So we're going to assume that these moments themselves have a polynomial expansion in terms of the fields. And then we can map onto the Starobinsky equation. So the leading order Starobinsky equation is basically setting that the potential sets the omega sub 1 terms. Okay, here I'm allowing myself a general polynomial potential. If it was just phi to the fourth, there'd just be one term here. And this omega sub 2, which is the first non-trivial term with the first non-trivial derivative, is set by the Hubble scale, okay? And generically, if we want to go beyond leading order, then we want to find contributions which give us higher order noise. And so that's going to look like higher polynomial derivatives here, okay? So let me give you a concrete example to show you how this works. So we're going to start with lambda phi to the 4 in the UV. And I can just plug into the Starobinsky formula. I have the equilibrium solution looks like this. And we see that phi at equilibrium scales like 1 over lambda to the quarter power, okay? So this tells us that we have a perturbative expansion in terms of lambda, where now we know the scaling of the phi's that appear in this generic formula here. And we can compute the corrections to these omegas order by order in perturbation theory, so we know how they scale too. Okay, so basically the claim is that these omega terms scale like lambda to the n plus m, and so we can use this to systematically organize what the terms that are going to appear in this Fokker-Planck equation look like. So at leading order, we just have Starobinsky. At next to leading order, the right-hand side, the new terms scale like order lambda, and we have two new types of terms. We have a term with two derivatives in it, and we have a correction to the one derivative. I'm sorry, we have a correction to the two derivative term that was here, and we have a correction to the one derivative term here. The first contributions to the quantum, new types of contributions to the quantum noise only appear at next to leading order, order lambda to the 3/2 in this power counting. And that's, we again get a correction to the two derivative term, a correction to the one derivative term, but now this new contribution appears, which has three derivatives. Okay, so how are we going to actually calculate these things in perturbation theory? So this comes back to the formalism that Dan and I developed now a couple of years ago, which we call the soft de Sitter effective theory. So this is complementary to the more famous effective theory of inflation. It basically applies in the limit that the wavelengths become small compared to Hubble. So here's a picture for the limit we're talking about. We have physical modes given by k divided by the scale factor. And basically, we're integrating out these short distance fluctuations inside the horizon, and we're looking for an effective description of these long wavelength modes whose wavelength is long compared to the horizon. These are the modes that typically freeze out during inflation, right? And then come back and are the seeds of structure today. So in terms of these scales, where the soft de Sitter effective theory lands is it's basically relevant as soon as you're talking about energy scales below Hubble, okay? And here I'm just showing, I'll come back to this kind of, but here we're gonna look at two different choices of the scale for these interactions in a bit. Okay, so what does this look like? We take the full theory action expressed in de Sitter space, okay? So this is with the FRW. And we can write this, right? This is just lambda phi to the fourth, where we have non-trivial curvature here, and this is coming from the measure. And the soft de Sitter effective theory is basically taking the long wavelength limit of this theory, and where we get is we get to something which is a first order action written in terms of phi plus and phi minus. I'll define those in a moment. And then we get a tower of polynomial interactions. So what are these phi plus and phi minus? They're the two IR degrees of freedom that come from solving the Klein-Gordon equation in de Sitter space. And they're in the cosmology literature, they're often referred to as the growing mode. So we'll call that, that's the one we call phi plus, and the decaying mode, which is what we call phi minus. And it's the correlators that determine the observables for the CMB, for example, come from the growing mode, okay? Because basically the point is both the growing mode and the decaying mode decay over time, okay? Their correlators decay as a power law, but the growing mode decays more slowly than the decaying mode. And so you can basically at late times, which is where our observations are being done, the growing mode is the only one who's still around. And the relationship between the phi field that exists in the full theory and these effective field theory fields is this one, okay? This again comes from just solving the free Klein-Gordon equation and de Sitter. And what we've done here is we've identified the tree level time dependence, okay? Remember, A is the scale factor, which depends on time. And so we have the scaling for the growing mode and the decaying mode is different as promised, right? This is again the statement that the growing mode decays slower than the decaying mode, okay? And what this redefinition allows us to do is it allows us to factorize the time dependence in these loop calculations. So the technical problem here is that if you were just working with the full theory fields, you solve the Klein-Gordon equation in de Sitter, and you get Hankel functions. And those Hankel functions are functions of momentum and time. Okay, we work in this mixed momentum time formalism. And when you need to use those mode functions, you glue them together into loop calculations and you integrate over both the momenta and the time in the loop. And it becomes very confusing to try to identify what's the UV limit and what's the IR limit, because you've broken Lorentz invariance, time and space are on different footing. And so so you really would like to be able to factorize this. So you just have time dependence times momentum dependence. And that's what that's really what the soft de Sitter effective theory allows you to do. Okay, so in defining this, the degrees of freedom are this phi plus and phi minus. We have a power counting in this effective theory, like any good effective theory, which is K over AH, okay? So again, remember that K over A is the physical momentum of these modes, and we're looking at the long wavelength limit with respect to Hubble. So it's a K over AH expansion. We have symmetries. So we have space-time symmetries, and we have a reparameterization invariance that comes from basically the ability to redefine var phi plus and var phi minus. And a new feature in this effective theory is you have to specify the initial conditions for the correlators of these fields at the horizon. So because we're integrating out all of the degrees of freedom inside the horizon, they leave an imprint on the horizon in terms of initial conditions. And this is one of the new features in this effective theory, which is basically how, people have often, the issues of apparent non-locality that come from inflation, right? The fact that we have correlations on superluminal scales is essentially captured or encoded by these initial conditions. So these initial conditions exist, on the entire Hubble surface, and so they're sort of non-local in that sense, right? And then that information gets propagated into the soft modes, which are the ones that freeze out. So other than this twist, this initial conditions, it's a very close analogy with heavy quark effective theory. In fact, this project was super fun. Basically, the way it worked was Dan would teach me details of how to do loop calculations in de Sitter, and I would teach him about heavy quark effective theory, and we would figure out how to make these two languages talk to each other, and that led us to this effective theory description. So I'm not going to go through all the details of that paper, but if you look at it, especially if you're familiar with heavy quark effective theory, it's following exactly the same strategy. So at everything in a heavy quark effective theory, there's an analog in this soft de Sitter effective theory. Okay. So let's see what to do in 10 minutes.
Oh, Tim, I mean, you can take a little more time if you want. It's okay.
Okay. Yeah, I'll try not to go too much longer than that.
Yeah, that's fine.
Okay, so everything I said was completely general for a scalar field in a de Sitter background. But what I haven't told you yet is how the matching works and what sets these scaling parameters alpha and beta. So if we go back here, right, I have this scaling alpha and this scaling beta. The way to calculate alpha and beta is, again, you solve the Klein-Gordon equation in the full theory, okay? You find this time dependence, and you can just match these alpha and beta coefficients. And it turns out they're set by the mass parameter. So as I take the mass to 0, the alpha parameter correspondingly goes to 0. And the power counting works such that all of these tower of interactions where I have any number of the phi pluses and one of the phi minuses, they all scale as power counting parameter lambda to the n-1 alpha. And so that goes like alpha to the 0 when alpha goes to 0. So in the massless limit, there's an infinite tower of marginal interactions that appear. And that tells us that we can get non-trivial operator mixing through renormalization group evolution, right? We have an infinite tower of operators, all with the same dimension. So you would naively expect they're going to mix under renormalization group evolution, okay? And from this action, including the kinetic terms, we just have this equation of motion relating the time dependence of phi plus to the tower of interactions. So if we look at the, if we basically take composite operators, which are phi plus to the n, then, like I said, we expect these operators to mix, and we can compute that explicitly. So we want a correlator, including one of these operators with n legs, and that includes a contribution where we tie two legs together, and that gives us a loop, which looks like this, okay? So here, I'm of course hiding a lot of details. This is all pretty technical stuff, but the point is simply by contracting any two legs, I basically get one of these loop momenta integrals, and notice that it's just a simple integral over momentum. That's because the soft de Sitter effective theory did its work already of separating off the time dependence. Now, for those of you who think about these issues in effective theory, right, you might recognize that what I have here is a scaleless integral. And when we're working with dimensional regularization, scaleless integrals vanish. And so in order to isolate the UV divergence, because I want to compute renormalization group evolution, I introduce an Irscale, and that lets me identify logs of this form, okay? So here, what I'm doing is very similar to dimreg. I have this alpha parameter, which I'm expanding around 0. And my 1 over alpha corrections always comes with logs AH. Just like dimreg, my 1 over epsilons always comes with logs of mu. And the game here is that by writing an RG, which sums essentially these logarithms, what I'm doing is I'm computing the time evolution of the long wavelength modes. And this is known as dynamical renormalization group evolution in this community. Basically, the point is that I can identify the summation of logs with time evolution. And so I get formulas for the renormalization group equations that look like this, okay? So here I have the time evolution is given by the classical piece coming from the equations of motion, plus this piece that I just computed in the last slide, okay, which you can think of as coming from renormalization group evolution. This formalism, it doesn't exactly look like it, but it is straightforward to show that it's equivalent to the Fokker-Planck equation that I showed you earlier for stochastic inflation. Basically, if you just identify your correlation functions of composite operators being essentially moments of this probability distribution. So this was explained nicely in a recent paper by Baumgart and Sundram. But it's, you know, if you go look in our paper, you know, we show a page of algebra how to get from this equation to the stochastic inflation equations. So this is a good point to emphasize, okay? And I know I'm just sketching everything. I haven't proven any of this for you, but the claim is that if we want to understand this Fokker-Planck equation, what is its origin, one way to see it is by computing the renormalization group evolution of composite operators in the soft de Sitter effective theory. And once we have reframed the question of understanding this Fokker-Planck equation in terms of RG, now we're very good at computing RG, right? And so we can just follow the standard rules and compute to however high of order we're interested in. And that's what we are going to do. So now I'm going to just flash some diagrams and some formulas. Again, I'm not, really explaining the rules of how to compute all these things, but I just want to give you a flavor of the kinds of calculations that we're going to do, which is going to lead us to understand the Fokker-Planck equation, including quantum corrections. Okay, so we're doing effective field theory. We need to do some matching. So at tree level, we just match our full theory fields onto these effective theory fields, and the matching looks like this. So we get both we get terms in the effective theory potential, and we also get contributions to the initial conditions. Okay, on this side, the 2-point function just gives us a Gaussian contribution to the initial conditions. Then we go to one loop. You'll recognize all of these diagrams, except that the legs are tied to future infinity. And this is this in formalism, this Schwinger-Keldysh formalism for computing correlation functions. So we have one loop corrections, right? This is a mass correction. And since it corrects the mass, that corresponds to correcting the alpha parameter in the effective theory. And so sure enough, we can show that this leads us to a shift in what we call alpha. And any other terms we generate at this order, we can remove by a field definition. Okay, we continue with one loop matching. Now we have the 2-to-2 diagram. And so this gives us loop contribution to the 4-point function in the effective theory, right, corrects the Wilson coefficient. And it also gives us some higher order impact on the initial conditions, but those aren't going to contribute to the order we're working. And then finally, we have a pure contribution to the initial conditions at order lambda squared. This is coming from a 6-point diagram like this. And this gives us a new non-Gaussian contribution to the initial conditions. So now we want to compute the RG. That was just the matching. Okay, so that defines the effective theory for us. It gives us the parameters in the effective theory as a function of the full theory parameter lambda. And so now we can take this effective theory action, we can start to tie legs together to compute the RGs. So that's what we'll do. We take this 4-point function, we tie 2 legs together, and this gives us operator mixing between phi squared and 2 phi's, okay? And again, you just follow the rule book for these in calculations, and where you land is a formula that looks like this. The details aren't important, just to say that there's a 1 over alpha squared and also a 1 over alpha term, and the RGs are summing these, okay? And so that's again capturing this log dependence. When we go to NLO, now we can tie together legs in these initial condition correlators, and this gives us, again, operator mixing between phi squared and now 4 phi's. And again, here I'm just writing, so there's a lot of terms here. Here I'm just writing the 1 over alpha contribution, since that's what gets resummed by renormalization group. And finally, this was the real beast of calculation to do. If you tie 2 of these legs together, you get composite operator mixing between phi cubed and phi. And again, there's a 1 over alpha contribution here. I should say, just because it was really very impressive, Akil, the student involved, he actually wrote a single author paper after this, where he studied this in particular by working in melon space. And we had to pull, we did this calculation 2 ways because it was really very tricky, but always we had to make some approximations, essentially doing an expansion in the long wavelength limit at intermediate steps. And Akil, using this melon space formalism, was able to do this calculation essentially without making any of those approximations. And it's a very cool paper. I recommend, if you're interested in this stuff, I recommend it highly. Take a look. Okay, so there's a bunch of diagrams and a bunch of formulas. We can put it all together to compute stochastic inflation for this scalar field to NNLO order, which is the state of the art. And you get a nasty looking formula like this. But then, and let me just highlight, after you do a field redefinition, okay, it puts it into a relatively compact form. We have the original Starobinsky dependence on the potential as promised. We have this original quantum noise contribution. And then we have this new term, which is this higher order correction to the noise. And again, the detailed formulas are here, but the point is simply that going to next to leading order, we actually were able to compute this, this new contribution as promised.
Sorry, just to
So-
clarify. So this equation is valid for modes with wavelengths which are over horizon, right? Or like with.
Correct. Yes.
But then, like in your previous formulas, what was this parameter Kkir, right? Which appears in the logarithms, and how does it disappear in this final equation?
Yeah. So
Well-
you should think of KIR as it's just a parameter that allows us to isolate the UV divergence, right? So so what we want to do, right? What are we really doing? We're using effective field theory to convert IR divergences of the full theory into UV divergences of the effective theory so that we can use the renormalization group to resum them, right? Because if you just do fixed order calculations in the full theory, you encounter logarithms of AH, and those logarithms can become large in the long wavelength limit, or in the
Yes.
late time limit, right? They go
Yes.
to infinity.
Yes.
And so, so this is the standard EFT trick. We recognize those logarithms as UV divergences of the EFT, and then we can just use the standard RG formalism to resum.
Okay, so KIR is actually some sub-horizon scale in the description. Is that correct?
No, KIR is some deep IR scale, but it doesn't matter, right? Because all it's there to do is to take scaleless integrals which vanish, make them scale full, so that we can isolate the UV divergence. Right? Because the RG sums logs from UV divergences. So this is what we all I mean, this is the story. It's not how it's always presented, but this is what effective field theory is really all about. Effective field theory is taking IR divergences of the full theory and converting them into UV divergences of the effective theory through matching. And then because we have UV divergences in the effective theory, we can use the RG to resum them. That's the claim.
So could I is it also similar to saying that there's no log phi here terms because they got absorbed into the renormalizing the couplings?
Oh, there's been a lot of, so there's a lot of processing to get to this point, right? Remember the RGEs are computed for the correlation functions, and then we need to convert the correlation functions into this probability distributions, right? By integrating, that was this, right? So we need to integrate this across phi.
Oh.
Yeah, so it's totally not, it's not at all obvious how, like I said, there's a lot of processing to go from something that looks like RG to something that looks like the Fokker-Planck equation.
I see. So there were log phi terms like you would get, say, in a Coleman-Weinberg potential.
So no, it's that the you should think of this as like, this is an exact analogy with the d log mu derivative that you're familiar with from standard RG.
I see. So you've taken out the log. I see.
So we've taken out the logs. Exactly.
Yeah. Okay. Yeah. Okay. Good. Thanks.
Yeah. Great question. Thanks.
Okay. Another question. So
Yes,
maybe
please.
related to Andre's question. So the scaleless integral vanishes because of the conservation of the UV divergence and IR divergence that you can phrase in that way, right?
Right.
And you said that within the EFT, you separated this UV divergence from the IR divergence by introducing this KIR, and then the
Yes.
resum that contribution. And then am I correct that you also have the IR divergence within the EFT because you now separated this cancellation and just resum this UV part?
Yeah. So what this is doing is this is capturing a resummation of the log of the IR logs of the full theory.
Yeah, that
Right.
I understand.
So
and
the
that is
full-
corresponding to the and that is corresponding to the UV divergence of the EFT, right?
That's right.
And then because originally it is the scaleless integral, I thought that there is the UV divergence and also the IR divergence within the EFT. But
Yeah,
maybe I'm wrong.
but we're not doing any fixed order calculation here, right? We're just computing the renormalization group evolution. So you would have to
Mhm.
worry about delicate cancellations of IR divergences in the EFT if you were computing something to fixed order, right? But here we're just focused on resumming logarithms, and so none of those issues are coming are an issue. None of what you're asking is an issue for this calculation.
Okay.
Right? We're really sorry, I'm just going to say it again, but right, the goal here, we know in the UV theory, we get these logs AH, right, emerging, and we identify those as being IR logarithms. And we just want to resum them so that we can improve the convergence of the UV perturbation theory, right? So that's what this formalism does. And that's what Starobinsky was really doing. He was really doing renormalization group evolution. It's just that it doesn't look like it because the renormalization group evolution is tied to the time dependence because the logs are logs of time, right? Logs of A. And so that's really the deep insight. And people have said this for a long time. There's been a lot of people making the connection between Starobinsky and some kind of renormalization group evolution. If I may be so bold, I would say that, we're the first, the soft de Sitter effective theory makes that extremely precise and systematic for the first time, right? So people knew how to do this sort of at leading order. Even there are some next to leading order calculations, but nobody besides us has ever done this. And in particular, no one's ever derived this correction to the noise before.
Yeah, so I think philosophically, or the idea I understand, but I think I'm just confused about some technical point, like, how it works in practice. Like, if you separate the UV divergence from the IR divergence from the scaleless integral, then I'm just worrying about what happens to this IR divergence in practice. Like, I think the idea I understand, but and maybe my question is more like a technical.
Well, it's just that we're not calculating anything that, like I said, we're not calculating any fixed order correlators here. We're not calculating any correlators, period. We're just trying to resum logs. Right? So the question you're asking would be like if I'm computing, say, 2 to 3 scattering in QED, right? Like E plus E minus goes to mu plus mu minus gamma.
Oh, okay.
Right? But that's
so
not what I'm calculating. Yeah. I'm calculating the running of the couplings, if you like.
So in a sense, okay, I see. Okay, I see.
Yeah.
So that doesn't have any IR divergence, and you can just follow this.
That's right.
I see. Yeah. Okay. Yeah, thank you.
Yep. Great. Okay. I'm already 7 minutes over. So the whole point of this, okay, I wanted to give you a flavor for how we do these calculations, what the technology we developed was, but in particular, when we applied the formalism to this first example and computed this next to leading order equilibrium distribution for just a light scalar field in static de Sitter space, we encountered no surprises, okay? We just worked hard, we computed this two-loop diagram, we extract the divergent part, compute the RGEs, solve them, done, okay? We got corrections to the probability distribution. I'm not gonna write the formulas for you. They're not particularly illuminating, but they exist. You can see them in the paper. And we could compute dynamics. So we can compute what's called the relaxation eigenvalues, which is basically the leading time dependence that brings you back to equilibrium, okay? And everything is well behaved. There's no issues. Everything follows power counting as expected, okay? So now what I want to do next is apply this formalism, go back to the EFT of inflation. Now I want to apply this to the inflaton itself in the presence of non-Gaussianity. Okay, so now instead of phi, I want to talk about zeta, right? That's the scalar metric fluctuation in inflation. And zeta also obeys a Fokker-Planck equation, okay? But zeta has a nonlinearly realized shift symmetry from the diffeomorphism invariance. So the only types of corrections that can appear in its Fokker-Planck equation are derivative corrections. And so again, we can determine the correlators of zeta through this operator mixing approach in the soft limit, okay? And just like before, we get the following types of contributions, okay? So the sort of order zeta squared contribution, the 2-point function is just coming from the Gaussian. So this is the Gaussian scale invariant power spectrum, right? That's the initial conditions. And again, we get logs of AH, okay? But the new ingredient here is if we include the leading non-Gaussian interactions in the EFT of inflation, so these are the leading non-Gaussian corrections you would get from any single field slow roll model in the UV, there are basically two
types of contributions. There's a phi dot cube term, and there's a phi dot times spatial derivatives. Sorry, I said phi. Zeta dot cube term and a zeta dot times spatial derivatives of zeta. Okay, there's 2 parameters in this model. We're going to get to my 2-parameter plot in a moment. And we can just compute the corrections from these contributions, okay? And this is just to show you that it's some concrete formula, okay, that we can derive. Now we can process this into a Fokker-Planck equation, now including these non-Gaussian corrections, okay? And if we assume that we start with nearly Gaussian probability distribution, then we get no particular surprises. Okay, so the 2-point function is just set by some scale. And then once we have that, we can infer all these other scalings. And basically, the punchline is that the leading correction is order 1. The subleading correction, this one, is suppressed by h over capital lambda squared. So we can solve this for a Gaussian distribution. We can take the Gaussian limit, we can solve this, and we can actually compute the Gaussian probability distribution concretely. It looks like this. And we can use it to compute the onset of eternal inflation. So this is from classic papers of Nima and others. And so you can basically compute the probability for reheating by integrating this probability distribution from -infinity to 0. So I'm rushing. In the last slide, we set the reheating surface to be 0. Okay, so we use the method of images to get a solution so that the field vanishes at 0. And so this just gives us the probability of reheating. And as time goes to infinity, in the Gaussian theory, the probability of reheating, basically everybody reheats, okay? And we can compute the volume of the reheating surface in this model, and it basically gives us this correction. So it tells us that there are 2 contributions. There's the this Gaussian contribution, and then we can, so we can compute the volume of this reheating surface. Okay, it's just integrating the probability distribution over the measure, and we get something which depends exponentially on time, and whose sign depends on the size of the 2-point function. So when the 2-point function is big enough, bigger than 1/6, the exact value doesn't matter, the reheating surface diverges and we get eternal inflation. And I actually think this gets to Keith's question from earlier in the talk. I think this choice here of normalizing the 2-point function may be the way to relate to that choice of initial conditions for where you start the scalar field. I'm pretty sure that's how that mapping works. Now, if we include the non-Gaussian corrections, again, we solve this thing, and what we get is we get some correction to the Gaussian probability distribution. And now we can ask again about the volume of this reheating surface, and we find that this volume diverges, which is the signal for the onset of eternal inflation, when this condition is satisfied. And the interpretation here is that we have this Gaussian contribution, we have this new non-Gaussian contribution, okay? It depends on 2 parameters, the speed of sound and this so-called C3 parameter. And so now we have these 2 limits, which I flashed earlier. We have the limit when the new physics scale is much above the pion decay constant. There, no problems, everything is fine. But we have this other regime where we take the new physics scale to be below the pion decay constant. And in this case, the claim is that the corrections are out of control because we find that the corrections are proportional to this ratio of scales. So the paradigm was supposed to be that we could take the range of allowed values for this scale associated with the non-Gaussianity was supposed to be anywhere in this range. As long as it was above Hubble, there was no problem. And what we're finding is a surprise. We're finding that if we take this scale below the scale of slow roll, the pion decay constant, then we're no longer able to capture these corrections systematically in perturbation theory. Essentially, we expect that there's a tower of these corrections, which are getting larger and larger, right? Just because they're proportional to f pi squared over lambda squared. Okay, and so that brings us to this final plot where we're plotting this blue region. Okay, there's a change of variables, but this is the same 2D parameter space. And so this blue region is the region where it seems like eternal inflation is happening in this model. But as I was arguing here, this is in the region of parameter space where maybe what's happening is that the effective field theory is breaking down. So it's the interpretation of this is subtle, okay? It could be that in this region, we would be in eternal inflation. If our universe lived here, then we would be in an eternally inflating regime. Or it's more likely that what's really happening is that the onset of eternal inflation is being dominated by these large fluctuations in the tails, which are being sourced by this primordial non-Gaussianity, and that there's a large energy associated with that jump in some way that we're trying to make precise now in our ongoing work, and that's what's causing the breakdown of the effective field theory. Because we followed all the rules to get here, and at no point did a scale emerge which was above the scale of the effective field theory. And so, so we're, again, our best guess for what's happening here is that there's actually a large energy associated with these fluctuations, and that we're basically pushed outside the regime of validity of the EFT, even though we thought we were doing everything self-consistently in the EFT framework. Okay, so I'm almost 20 minutes over. I'm gonna stop there. I'm happy to keep chatting. I've got all day, so we can go back through things slower, or I'll take any questions you have. Thanks very much for your attention.
Yeah. Great talks.
So you're saying then that you can't, that the result that you get, you can't trust in the end. That's what you're saying there, right?
Yeah, it's really puzzling because there are people take these models and they've calculated the tails of the distribution. So one application, very similar type of work, is to try to compute the spectrum of primordial black holes from inflation. So if you turn on primordial non-Gaussianity, then you can get large fluctuations, which give you primordial black hole production. So this is something people talk about. But it seems like the fluctuations which matter in the tails are potentially pushing you outside the regime of validity of the low energy approximation. But there's no, the thing that's very confusing about this is that it's not like an energy scale. We're trying to model this in some toy settings. We have some ideas, but nothing super concrete, where you could actually understand that, if you start, say, near the origin, and then you find non-trivial probability to be way out in the tail in a short amount of time, you can imagine that kind of jump in field space is associated with high energy. And then that would tell you that would give you a physical reason why the EFT is breaking down. Right now, we don't have a sharp way of saying. All we have, right, we have this formula, which looks like it doesn't hold even in the regime of parameter space where the EFT is expected to be good. So probably what we've done is we've captured some high energy fluctuation, right, which is pushing us outside the regime of validity of the EFT, but but again, it's not like when you do standard EFT, say at a collider, and you know if you collide the particles at the energy above the scale of the EFT, that all hell's going to break loose and the thing's going to break down, right?
Yeah, well, I was going to ask you, is there a heavy quark analogy here or not?
Not one that I mean, you know, maybe actually. Okay, so this is a I don't think that this is a direct connection to this problem, but you know, soft collinear effective theory was first discovered because heavy quark effective theory breaks down at the endpoint of the distribution.
Mm-hmm.
When you compute, like, say, the spectrum for heavy meson decays to light meson plus gamma, you compute that spectrum of gamma as a function of energy, and you find that at the endpoint of that spectrum, you encounter new large logarithms, right? And those are logarithms coming from soft and collinear divergences, right? So it could be, I mean, that would be amazing if there's yet another EFT that emerges in this limit that is an EFT to describe the tails.
Yeah, so you should be subtracting out these logs then. That's basically what should be happening, right?
Yeah, maybe. It's, or some other degrees of freedom need to come in order to, to basically turn over whatever this divergence is, right? But we're even puzzled at this point of, again, I keep mixing these terms. In the soft collinear example I just gave, you could identify the kinematics. And once you, especially in hindsight, it was very obvious that you were in this regime where soft and collinear divergences were important. Here, because of all this processing into this probability distribution, there's no kinematics anymore. And so it's sort of hidden where the issue is, right? So that's what we're trying to do. We're trying to untangle, I could, anyway, we have a ton of ideas. I could entertain you for a while, but like, for example, we do this Cramer-Moyles expansion of these transition amplitudes. So perhaps what's happening is that expansion is breaking down. And maybe what we need to do is we need to be able to compute those things non-perturbatively in order to accurately be able to capture the tails, the fluctuations in the tails, right? That's one place we put our finger on where we're making an approximation that could be failing, right?
I see. Yeah. Thanks. Yep.
A naive question. So in principle, there are observational constraints on primordial non-Gaussianity, right?
Yeah, very good.
And my understanding was that in the context of primordial black holes, for example, that it's supposed to be some large fluctuation, large non-Gaussianity at a specific momentum scale, right? That enters the horizon at some point and enhances the black hole production, but this shouldn't affect like CMB or other things. So, and in your story, it looks like this large non-Gaussianity is a sort of universal, or
it's good. So so I brought up the primordial black hole production. That's another place where, or that's another setting where people are computing, where the physics of interest is dominated by fluctuations in the tails, but they're typically using quite different models than this, right? So they might, so for example, right, they'll, as you probably know, they'll like introduce a kink at some point in the inflaton potential, right?
Yeah, which was related to my earlier questions, that in principle it can come from classical, from tree-level potential, right? So that's a classical effect in a sense.
Yeah, and so I don't know, it could be that there's a way to do it. I'm not an expert, so I don't know how to incorporate those types of potentials into the EFT of inflation. My intuition is that if there's a sharp feature in the potential, that breaks the slow roll approximation, and so it doesn't map onto the EFT of inflation without some new ingredients, right? So we were using the EFT of inflation in order to parameterize leading non-Gaussian contributions, where what we have in mind, right, is like phi to the fourth theory is the theory of inflation, for example, right? Because that gives you primordial non-Gaussianities. And so, so this is just mapping this, right? In this EFT of inflation limit, the leading non-Gaussianities are, there's just two parameters, so it's tractable, and we know the operators, so we could do these calculations. But yeah, there's a much broader setting for these kinds of questions, certainly.
Yeah, okay, but then doesn't it mean that this eternal inflation sourced by large non-Gaussianities is ruled out because large non-Gaussianities are not
yeah.
observe them?
So that's what this plot is supposed to illustrate. So so these red contours are the current Planck constraints in this parameter space. And so you can see, right, this blue region where we're finding this puzzle, or where, you know, potentially we're seeing this phase transition to eternal inflation, you know, is within the sort of one, you know, 2-ish sigma region that could be, certainly it's allowed by data here, right? And optimistically, you can hope that the data lands up here. But this is really to illustrate, and I didn't say anything about this. This is not our calculation, but this perturbative unitarity bound is an attempt to try to take the EFT of inflation and compute essentially the analog of you know, the longitudinal W scattering calculation that we know and love in the standard model, right? To find the scale of perturbative unitarity violation. It's much more complicated than that, but that's basically, this is another attempt to try to understand where is the good region of parameter space where perturbation theory holds. And so the claim is inside this region, and this is, by the way, a very conservative calculation. We could talk about it, but inside this region, perturbative unitarity is expected to hold for the EFT of inflation. And again, that overlaps non-trivially with the allowed region of Planck and with our new region here, where we're encountering these large tails, or where these large tails are dominating the physics.
I see. And also, just to clarify, you did not study systematically like corrections to the slow roll, right? So this was this is another thing.
Yeah,
okay.
This is exactly, that's another.
Yeah, again, can I? So again, going back to the breakdown of this EFT. So do you think that it's kind of similar to the finite density effect? Because I know one example, like, you know, if you have just a phi to the fourth theory without, you know, just forget about the inflation, just phi to the fourth theory. And if you have the bunch of the phi particles in your background, then even if lambda itself is small, then the expansion parameter will become lambda times the occupation number. And if the occupation number is large, then you have to resum this, right? And then in your case, you know, you're talking about the large fluctuation region in a sense. So that sounds kind of similar to this, you know, large occupation number case. So do you think that like it's kind of related, or I don't know?
That's an excellent comment. Yeah, that's one of the things we've been thinking about is, so there's this recent work by Riccardo Rattazzi and collaborators trying to basically just, so what they're doing is they're taking the large charge, this sounds like a digression, but it's actually related, I think, to what you said. So they're looking at basically evaluating correlation functions in the presence of large charge. And they're finding that there are new saddle points in the path integral that they need to include in order to capture the leading corrections from large charge. So we are optimistically wondering if, exactly as you say, maybe we are working in the wrong saddle, and that the tail is very much in the spirit of Rattazzi et al., that in order to properly calculate the tail, we actually need to expand around a different saddle point. And maybe it's one of these large occupation numbers type saddle points. Exactly.
I see.
I just don't know how to make that, you know, we've been studying these Rattazzi papers, but I don't know how to make it precise yet. But that's, again, that's related to this idea that it's, you know, a sort of long, it's like a big jump in field space in a short amount of time, right? And so it's a qualitatively different effect than, you know, what this formalism is built to capture, which is the, you know, and let me say, I didn't say this yet. I spent all this time on the lambda phi to the fourth example in order to provide some context for the fact that this formalism works in that case. And we think the difference is because there's a potential for phi to the fourth, right? So, you know, phi to the fourth has this non-trivial potential, which is basically keeping you near the equilibrium probability distribution. So yeah, we calculate corrections, it moves the shape around a little bit, we calculate the noise, right, which changes the evolution a little bit, but at the end of the day, it's all perturbation theory, and everything's going to be dominated by the classical rolling back to the middle. And that's what we find in the, when we compute these relaxation eigenvalues and so on. There's just no issues. The probability distribution makes sense. But in this other setting, when we apply this then to the metric fluctuations of the inflaton, now there's effectively no potential, right? We assumed a shift symmetry even. So we really were turning the potential off. And so now nothing is sort of preventing you from making these large jumps, right? You don't have the potential kind of localizing you towards the origin. And we think that somehow fundamentally that's the deep difference between these two calculations. But again, we're following all the rules of the EFT game. And so, what this really is signaling is some new type of breakdown. Right? And that's why we're excited about this, is because, if we can crack that, then we can understand, potentially a new condition that you have to satisfy, right? When you're, when you want to apply the EFT.
I see. And also another question. So in the case of the usual skate, then we know that this, IR divergence are coming from this soft region or collinear region, but do you have any kind of intuitive explanation of why we're having this IR divergence in the zeta space?
Yeah, so it's, I mean, at some level, these theories have soft divergences, right? So it's exactly in the sense that, QED has both a soft divergence and a collinear divergence, right? It's pretty easy to see at tree level. There's an exact analogy here. It's just there's only a soft divergence. So when you take the momentum to 0, right, you get divergent diagrams in the loop expansion, which give you these logs.
So the IR divergence is coming from the soft region, and then there's the scale Hubble, so that appears in the log.
Exactly.
I see.
Exactly.
Okay.
It's exactly the same kind of physics, and it's the and the thing is that it's I mean, the breakthrough I can't emphasize enough. The soft de Sitter effective theory is extremely powerful because it allows you to see the soft limit very directly. In the full theory, because the mode functions involve both time and momentum, it's tricky because the order of limits issues are tricky, right? You want to take the late time and soft limits, right? But exactly how, when you do the loop calculation, right, you integrate over both. And so there's regions of the integration where one is large and the other is small, and vice versa, right? And so it's actually tricky to extract the soft limit when you just stare at the full theory. Everybody always says that these logs of AH are IR logs, right? But it's only made manifest when you write down this EFT.
Okay. Yeah, thank you.
So is there any physical system which is also described by the same type of the Fokker-Planck equation without the potential, but for which we have more understanding on how it behaves and which we could
Good. Yeah.
be useful?
So in some of these great earlier papers on the phase transition to eternal inflation, they actually study they call it a bacteria model, but they basically discretize this system and they study the sort of growth of these bacteria, and they have a boundary where they all die, and right. And so that's the closest analogy I know to some other physical system. And it captures a lot of the essential features. But we've been avoiding trying to exactly go down that road because we think we understand the solutions to the Fokker-Planck equation, and that we already see that there's something breaking down, and so we don't think that necessarily that description is going to help us, but there is some nice work on some toy models like that.
Okay. But I was meaning more like, something condensed matter or something which was really studied. I mean, maybe somebody has studied it before and there is understanding already. We just don't.
Yeah, it could be that. Yeah. I'm not aware of anything though. Yeah.
Okay.
Yeah. Okay. Okay. So if there are no more questions, okay, then let's thank a team. Okay.
Thanks, everyone.
Thanks.
Thanks, Tim. It was very
Yeah,
nice, Tim.
thanks.
This
Yeah.
was really fun.
Awesome.
I
It was